Thank you all for coming to Quantum Computing with Amazon Braket, from exploration to enterprise. My name is Eric Kessler. I'm the general manager of Amazon Braket, our quantum computing service by AWS, so you're going to learn more about that. But I'm very excited to be joined today also by Michael Brett. He's the head of go-to-market for quantum computing at AWS. And yeah, we're going to give you a little bit of an overview, what we are been up to at AWS, how we see the industry evolve, and what you can do today already with this technology. To give you a little bit an overview what to expect today, I'm going to give you a little bit of an introduction of what is quantum computing and where are we today. Then we're going to go into a bit of an overview of what we're doing at AWS before we dive into hybrid quantum classical workloads and how we're supporting these type of cutting-edge workloads at AWS. And finally, we're looking at one particular customer case study, which was about drug design with AstraZeneca. And finally, we're going to show you how you can get started with quantum computing. But I wanted to get out of the gate here with addressing a very common misconception about quantum computing. Namely, a quantum computer is not a classical computer that just runs a little bit faster. As a matter of fact, quantum computers are actually very slow compared to the clock cycles from classical computers. Instead, a quantum computer can run a richer class of algorithms compared to classical computers. And you may ask, why do we need a richer class of algorithms? You know, we have our classical algorithms and they work just fine. Well, it turns out there are certain types of applications where all the algorithms that we know require an exponential overhead as the problem gets bigger and bigger, exponential in the time that it needs, the memory that it needs, other resources that it needs, right? And one of the prototypical problems of that kind is to simulate quantum systems themselves, right? So this is kind of the home turf applications of quantum computers. Because when we just look at the system, say particles, electrons, that interact with each other, behave quantum mechanically, if we want to simulate them with a classical computer, already 50 of those particles require supercomputing scale classical compute. And because it is exponential, if we go from 50 to 100 particles, it becomes completely out of reach for any computer today and in the future, right? And of course, this idea is almost the founding idea of quantum computing and goes back a long time now, from 1981 by Richard Feynman in this very famous quote where he said, nature isn't classical, and if you want to make a simulation of nature, then you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy, and that's true. It's actually a very hard problem to build a quantum computer, and the technology is still early, but we're seeing a lot of improvements, right? So as the take-home message, quantum computers can solve some problems with exponentially fewer gates or fewer operations than classical computers because they use different types of algorithms. So to put it kind of very provocatively, it's not a 2x speed up, but a 2 to the power of x speed up, right? And because it's exponential, that's the difference between something that's possible and something that's not possible to compute. So from that very brief introductions, there are actually some very profound learnings or lessons we can take, right? Because quantum computers are not just a classical computer that runs faster, it means also that quantum will not replace classical computers, right? If you have a classical algorithm that does not scale exponentially, that works well for the problem that you have, there's no argument why you would replace it with a quantum computer because they're generally slower, they're generally more expensive. The second point is that many use cases of quantum computers are hidden by definition. And what do I mean with this, right? Like if you look around at your company and think about what are the applications that a quantum computer could be used for, chances are there are some applications you don't see because they are not possible to solve with classical computers today, right? Because by definition, we want to apply quantum computing to problems that are hard for classical computers. And the final one is, because we're talking about a new class of algorithms, these applications are not just lift and shift, right? When we have a quantum computer at some point in the future that can address industry-relevant problems, we cannot just take what we were running on a classical computer before and move it over to a quantum computer and it will work. These are completely new algorithms, completely new primitives, and it requires a lot of talent and skills and IP to develop these kind of algorithms. And we're very excited about these algorithms because the applications are applicable to a wide field of verticals, right? So we already talked about the home turf kind of problems on the left-hand side, like problems where we try to describe nature for all intents and purposes in physics and chemistry, simulating molecules and reactions, etc., developing new materials and material science. But maybe very surprisingly, it doesn't stop there, right? Quantum computers are not only exponentially faster for these type of problems, for some of these problems, but there are also certain problems that are inherently classical, where it has been shown that quantum computers do provide an advantage. Well, maybe the most famous one is in cryptography, right, where the Shor's algorithm showed that you can factor large numbers exponentially faster than with a classical computer, right? This is relevance for RSA and encryption and so on and so forth. But then there are also problems in the space of optimization, and machine learning is a little bit more nuanced here, and a lot of research is being done in those topics. Well, all of this is to say that we at AWS really think quantum computing is a foundational compute technology. And like with other compute technologies, we want to bring these capabilities to our customers, and in the fullness of time, make them part of our offering, our compute fabric at AWS, right? So in some sense, our job at AWS is to make quantum computing boring, right? When you look at the accelerated compute portfolio at AWS, we have already different types of accelerators, from GPUs to AI and ML accelerators, ASICs, and FPGAs, and so on and so forth, from different providers. And in the fullness of time, I think quantum is just another type of accelerator. But of course, it's a long journey to that place. And to throw a little bit of cold water, I want to really stress that the technology is early, and today there is no quantum computer that can solve any industry-relevant problem faster, cheaper, or more accurately than the best classical alternative. So then, what are customers using quantum computers for today, right? Well, like any other technology, quantum computing will not start with the broad-scale adoption, but it will start from niche applications and gradually grow from there. And I like to make the analogy with GPUs, right? GPUs started for a very niche application space of graphics processing until researchers in academia realized they can be used for mathematical calculations, big matrix multiplications, and so on, until they finally got the broad-scale adoptions through AI and machine learning. And in the same way, quantum computers today, what most of our customers do is using quantum computers to study quantum computing, right? From researching the devices, the sources of noise, developing error mitigation protocols, to researching these novel types of algorithms, trying to understand how they converge, how they are impacted by this noise. So trying to close the gap between what the hardware brings from the bottom and what applications come from the top. But of course, ultimately, we don't want to just study the hammer, right? We want to actually use the hammer, right? Using quantum computers as a tool to solve problems in other domains. And the first areas where we will solve different kind of problems will be in the space of scientific applications, right? To drive new scientific discovery in high-energy physics, in material science, in quantum materials, and so on, before we go into this final step into broadly industry-relevant problems with broad-scale adoption. And we are at a very exciting time of the industry, I think, right? Like, we are just at that cusp of going over from studying the hammer to using actually the hammer, right? And against that backdrop, I wanted to introduce you to what we're doing at AWS to help accelerate that technology, to help to help make that promise of quantum computing a reality. So in a nutshell, our quantum technologies at AWS, we have 4 pillars. This is Amazon Braket, our quantum computing service. You're going to hear about that more. We have the Amazon Advanced Solutions Lab. This is a professional services team that focuses on quantum computing and related classical technologies. And then we have the AWS Center for Quantum Computing. It's a research facility where we're developing our own quantum computing hardware and quantum error correction technologies. And finally, we have our post-quantum cryptography team and quantum networking team that's part of AWS Core Networking. So let's start with a brief overview. So the AWS Center for Quantum Computing, already mentioned, is an AWS research center that's located at Caltech. We are building our own quantum computing hardware there with a quantum error correction first approach. So we really want to address that next level of scaling that is required to take the technology from studying the hammer to using the hammer. We're building on a technology that is dubbed CAT qubits, which combines superconducting qubits with resonators, microwave resonators, to suppress certain types of noise. And I'll talk a little bit more about that on the next slide. As a matter of fact, just beginning of the year, we showed and published results from our first prototype that's called Ocelot. There's a picture of the chip here. And we were able to show that through that architecture, this CAT qubit architecture, we are able to suppress a certain type of noise to a degree where the resources required to implement error correction on this architecture is 10 times lower than in the traditional approach. So we're very excited about these results. But of course, our approach is only one of many. Right? There are many other promising directions, from building quantum computers with ions that are trapped, building quantum computers with neutral Rydberg atoms, or photons, and many others. And at the same time, we believe that we need to bring this technology in the hands of our customers so that they can experiment with this technology, start developing algorithms, and start developing the IP around how we can bring the new applications and the resource requirements of them further down. And that was the reason for us why we launched Amazon Braket in 2020 at this point, right? We wanted to democratize quantum computing, bring different types of quantum computers in the hands of our customers so that they can learn, experiment, but also do research into applications and envision how quantum computers will be used in the context of AWS, in the context of existing HPC pipelines. And today, we provide access to third-party quantum computers, and in the future also, of course, our own AWS-built quantum computers in the fullness of time, all in one consistent experience. The quantum computers that we have available today is from 5 different providers. That is 2 ion trap providers, IonQ and Alpine Quantum Technology, AQT. We have 2 providers that are building superconducting QPUs with Rigetti and IQM. And finally, we have a provider that is building Rydberg-based quantum computers from QEra. So we want to give customers that choice and the ability to contrast and compare the different approaches. Each of them have different pros, different cons. It is not clear that this is a winner-take-all market by any means, right? There is a lot of different potential applications for each of these technologies because they have all very different characteristics and different programming paradigms. And we want to give customers that visibility into the technology. So then let's take a look at a 20,000-foot view to Amazon Braket. And we think about Braket in kind of 3 different layers, right? Like at the bottom, you have the infrastructure and the access modes, right? That we are providing access to QPUs, to quantum circuit simulators, as well as to the classical compute that is used with quantum computers in tandem. We're going to hear about that more from Michael. And we can access these quantum computers in different access modes. For example, on demand, just pay as you go as you use from AWS. You can also make reservations where you get dedicated time on a particular device where only you can access it at the time that suits you. In the middle part of the stack, we're providing the interfaces and capabilities, right? From Jupyter IDEs to programming tools, compilers, and a feature for executing quantum hybrid algorithms with hybrid jobs. And then finally, at the top of the layer, we want to bring different type of tooling to our customers that they're used to and want to use, right? We are supporting all of the major quantum computing frameworks, from IBM's Qiskit to Penny Lane and NVIDIA's CUDA-Q, as well as a whole list of software tooling and programming frameworks from our partners. Many of them are here at re:Invent today and giving their presentations, so I encourage everybody to check that out. But essentially, we're realizing we can't build it all on our own, and we want to make sure that anything runs on Braket, and we can bring the tooling to our customers that they want to use. And throughout that stack, we are trying constantly to improve the performance, make the user experience better, get more throughput performance and quality performance out of these early stage devices. And there's a lot we could talk about with the different capabilities. I picked out a feature that we just recently launched. This is Amazon Braket program sets. So the idea here is that the way you interact with a quantum computer is not that you send a single program and you get it back and you analyze it. In reality, a very common workload pattern is that you send multiple of these programs that either are related to each other, they can be the same, they can be somehow connected or also completely independent. And for each and every program that you send, you need to compile it, you need to have the I/O overhead of bringing it down to the control system of the QPU, load it onto the FPGA, and so on and so forth. So there is overhead in each of those steps. And with program sets, we're enabling customers to submit multiple quantum programs, a whole series of quantum programs in a single payload with a single API call, which allows us to optimize that payload, compile it, and gain efficiencies through compilations and I/O process, bringing multiple programs at the same time onto the FPGA. And for certain types of workloads, we're seeing up to 24x speedups with this feature. So with that, I want to come back to this kind of inverted pyramid of use cases. And as we discussed before, we think that the first use cases will be in the scientific domain before we go into broad industry adoption. And I don't want to downplay this as a mere stepping stone, because I think it's a very profound fact, actually, that quantum computers will change the way that we understand nature, that we can understand how nature behaves at the microscopic level. And in fact, a recent study from NERSC, this is a supercomputing facility from the Department of Energy, found that at least 50% of their production workload has the potential to be exponentially accelerated by quantum computers, right? So there's a tremendous opportunity to accelerate research and scientific work through quantum computing directly. And many countries and governments around the world are realizing this opportunity, right? So this was one study from NERSC. Other studies, for example, from LANL, find numbers between 30 and 50%. But countries around the world realizing that this is an opportunity to accelerate scientific breakthroughs and have founded national quantum initiatives to find those first use cases and then also use it as a stepping stone for further industry adoptions. And a number of those government initiatives, national initiatives, they're building with Amazon Braket, right? Because the first thing that they want to have is to give access to quantum computers to their local research communities. With Amazon Braket, they get access to HPC resources and quantum computers on demand. We build scalable and secure research environments, as well as tailored administrative and budget controls to run large-scale research organizations in the cloud. For example, we're working with the NQCH in Singapore, with the NQCC in the UK, QCloud in Ireland, and PAWSI in Australia. As a matter of fact, PAWSI just launched the Quantum Hub portal, which provides researchers access to quantum computing and classical computing resources through AWS with tailored administrative controls. And they're now starting to run the Cetonics Q pilot, where they will allocate quantum computing resources for local researchers to drive that innovation flywheel. And we're super excited about initiatives like this because we think there's a lot of research to be done, and by having access to real quantum computers, that research can accelerate. So, but of course, we are all very excited about bringing that technology also out of academia into broad industry adoption. And Michael is going to tell us more about that idea and how we're going to drive our customer engagement in this field. Take it away, Michael.
Thank you. Well, thanks very much, Eric. Wonderful introduction to Braket as a service. So Eric and I work very closely together. He builds and operates the Braket service. He makes it available to our customers so that you can use it through the AWS console. It's a service that's available in the cloud for you today. You can access quantum computers just in the way that you would any other service on AWS. So if you enjoy using EC2, you're going to love using Braket because it's just another service, but we've got quantum computers on there. My job is to talk to our enterprise customers about where quantum computing is headed and how they will be able to make use of this in the future, the kind of workloads that they'll be interested in, the thinking that they need to go through now to prepare their strategies for quantum computing in the future. Most of our customers today on Braket are researchers, as Eric mentioned. They're national labs, they're hubs, they are individual researchers at universities. Most of them are doing science. So they come to AWS to use the infrastructure that we've got available to do good science. So they're collecting data, they're doing physics research, they're doing computer science research, they're doing application and benchmarking style research. But as we build up this stack, we move from the science to looking more at solving industrial scientific use cases. So we'll give an example in a moment about drug discovery, but also think about materials design, think about production opportunities. But at the big scale and where we want to get to is how do we use quantum computers for large-scale enterprise problems in exactly the same way that we use high-performance compute classically today at AWS. So some companies are really starting to invest in this ahead of the curve. There are a few leaders out there that are really investing in quantum computing, in understanding those use cases and where the potential might be. One of those companies is JP Chase. We actually have another breakout session tomorrow, which I encourage you to come to, with JP Chase, where we will go through exactly how we operate the end-to-end application study and benchmarking work that we've been doing with them for the past couple of years. But their motivation is really clear. Marco Pistoia, who until very recently led the quantum computing program at JP Morgan, he's since gone on to a wonderful new opportunity at a quantum computing hardware company. But he said, if a company doesn't do anything about the market right now, when quantum advantage becomes real, it might be too late. And this is really important. This is a fast-moving technology. This is not just a lift and shift from an existing HPC workload to a quantum compute workload. These are complex algorithms, they're complex problems. They take some thinking to work through to design new approaches to running quantum classical hybrid work, to running workflows together. And so the leading organizations in enterprise adoption of quantum compute are really thinking about this now in anticipation of that future potential advantage. So here's the journey that we go through with them on it. We look at through a discovery process around use cases, helping them identify the kinds of workloads that are well suited to a quantum computer. We then research and benchmark with them the quantum computing algorithms. So we compare quantum on quantum. How does one quantum computing hardware system compare to another quantum computing hardware system? We also compare quantum and classical together. So how does the best available classical approach to that problem match with the quantum computing approach to that? And then look at the hybrid opportunities. What if we combine different things together and orchestrate across multiple different platforms on AWS to explore this space? And that's what pushing the boundaries is all about. How do we unlock the potential of end-to-end compute, so using a quantum computer to make classical computers go faster? And then that will lay the groundwork for us for production applications in the future. So bringing all this together, we want our customers to be prepared so that as soon as Amazon Braket gets bigger and we've got more capacity and we're scaling up across multiple regions, you are ready with your workloads to jump straight into that. So last year at reInvent, we launched a program called Quantum Embark. Quantum Embark is our sort of entry point for any enterprise customers to just get started with quantum computing. So if you're not quite sure what to do, you know you should do something, but you're not sure what that something should be, this is the program for you. So it is a 12-week, fixed price, fixed scope program to just get started in quantum computing and work with our teams to work through that process that I just described on the last slide. So the use case discovery, do some training and enablement together, and then deep dive on one particular problem. So let's pick one problem from your organization and solve it together. Go through the process to write out the quantum computing algorithms, compare it to the classical algorithms, fit it onto a quantum computer on Braket, benchmark it quantum to classical and quantum to quantum. That process takes about 12 weeks. We work as a joint team together. So some of our solution architects and applied science specialists around quantum computing, some of your team as well, and we bring that together. And the whole idea is that we're able to give you and your executive teams actionable outcomes without the hype. There's a lot of hype and excitement, and for good reason, around quantum computing, but how do we make it real for your particular organization? And so the Quantum Embark program is all about that, giving you some actionable outcomes so that you can understand if and when quantum computing is going to have an impact on your business, and then you can start to inform the rest of the stakeholders across your company about where that's headed. A little bit deeper, we've got a team called the Advanced Solutions Lab. This is our professional services team that engages directly with customers to do long-term R&D engagements around quantum computing. Our colleague Martin Schutz from the Advanced Solutions Lab will be on stage tomorrow at the breakout session I was mentioning with JP Morgan Chase to talk about exactly this. They had a 3-year program of effort looking at multiple problems across quantum computing at every level. So from optimization of how to use particular devices to compilation strategies to application benchmarking, this is a deep research team. So this team will design a custom R&D engagement for your particular needs. They'll work with you to develop and explore novel quantum computing algorithms. We'll look at opportunities to deliver business value today on classical compute hardware, but most importantly, generate that intellectual property so that you've got the know-how and the IP so that you can take advantage of quantum computing as it matures over time. So practically now, let's take a look at what does quantum computing mean for our entire accelerated compute portfolio. So if you are a user of AWS's high-performance compute services, where does quantum computing fit into that overall landscape? And the good news is that in some ways, Braket and quantum computing is just another instance of compute on AWS. It's just another type of accelerated compute. So we have CPUs, GPUs, other accelerated processors like Trainium and Inferentia. Well, quantum computing is just one more type of computer in that overall portfolio. And so we've been doing a lot of work this year to integrate Braket as another sort of instance type within the high-performance compute services of AWS. So you might be familiar with the parallel compute service, with AWS Batch, with Parallel Cluster. This is for classical HPC. So if you're the Formula One, if you're Ferrari, and you need to do computational fluid dynamics, those are the services that you're using to do those large, industrial scale, heavy compute workloads on AWS. They don't go directly to EC2 to spin up instances. They use these orchestration tools to do those large scale problems. And so we're looking at how do we integrate Braket directly into that. You should be able to go straight to the high-performance compute services and spin up accelerated compute instances of multiple different types that include quantum computing and orchestrate across that entire end-to-end workflow over time. So we've been doing a lot of work to integrate that into the systems, and the example that I'm going to show you in a second is based on exactly that framework. So think about AWS as the core infrastructure. We've got compute and networking and storage. Braket is just another form of compute on there. Different abilities to consume that compute over time. So on our classical infrastructure, we've got on-demand, we've got capacity blocks, we do spot, reserved instances. We're building out exactly the same for Braket over time as well. So right now, you can log into the console, you can access Braket on demand, you only pay for what you use, no upfront commitment to use a quantum computer, or you could reserve a capacity block next Tuesday at 3 p.m. to do your particular workload as well. So we really are thinking about quantum computing as just another computer within the framework that you're already used to running large-scale workloads on AWS. So let's take a look at what a large-scale end-to-end industrial strength workflow looks like. So this is a very typical kind of workflow for one of our high-performance compute customers. They might be doing drug discovery, computational fluid dynamics, some kind of engineering analysis, circuit layout, something like that. And there'll be some user action process right at the top that will flow down to an execution plan. There'll be some I/O on there. There'll be an orchestration layer handling different types of compute. But all of this numerical heavy lifting that's going on, that could be a couple of hours of work, a couple of weeks of work, a couple of months of work that's going on. We see everything in between. Excuse me. And the idea of quantum computing is, well, what if we could interleave some parts of that overall workflow that are well suited to a quantum computer? So we're still doing quantum and classical together, but in a hybrid modality. Can we get an end-to-end speed up? Can we reduce the entire operational end-to-end workflow of a large-scale high-performance compute workload and get a faster result for our customers and hopefully a lower cost result for our customers as well? So we're at the very early stages of putting this into practice. And we've got a great example with our customer AstraZeneca that we worked with earlier this year to explore exactly this kind of problem. And so this was a joint program that we did together between AstraZeneca, IonQ, the quantum computing hardware company that's on Braket, NVIDIA, and AWS. So it was the 4 companies working together, looking at the algorithm problems, the orchestration problems, how we bring that back together as an end-to-end workflow and to see what kind of result we could get there. And so the particular problem that we were looking at was this chemistry problem called transition metal catalysis. And it underpins so much of what happens in modern drug design. This is part of the everyday workflow that every drug company in the world goes through. And it's a really tough computational problem to solve. It is very difficult for a classical computer to simulate this because as the complexity of these molecules grows, the amount of connections between them also increases exponentially, and it becomes harder and harder to simulate that. But if we could simulate these accurately and early, then we could identify new synthesis routes before going to the wet lab, before doing that work, mixing chemicals together to see what would actually happen. And so the particular chemistry problem that we looked at here was something called the oxidative addition and Suzuki-Majorana coupling with the nickel catalyst. It really rolls off the tongue. But the idea here is that we're looking at a catalytic process. So we're going from that B state up to the BC state and then down to the C. And so that's an energy barrier that we need to get over. So we're modeling out what happens in the real world, in real chemistry, quantum mechanical process, going over this energy barrier through a catalytic state. And that determines whether the height of that barrier determines whether this reaction is going to run at all. So if it's too high, if it's too much of a barrier, when we go into the wet lab, that's not going to come together as the molecule that we want. So we want to understand before we go to the lab, the height of that barrier and what the end state is going to be. Solving that problem is really, really tough. This is the classical workflow for it. So we start with calculating an active space, and then there's something called the trial wave function, which is one of the hardest parts of this overall state. This is where the quantum bonds are being understood by the computers, and then we hand it off to classical systems to run some Monte Carlo analysis and find the overall energy state at the end of there. But it turns out that we can replace one part of this workflow with a quantum computing algorithm instead. And so working together, AstraZeneca, NVIDIA, IonQ, and AWS, we said, what if we went classical, quantum, classical? We put a whole bunch of, we adapt the classical algorithm to better suit a quantum computer, and then we also adapt the classical workload that happens afterwards. Can we get a better result from that over time? So we took a look at adapting that trial wave state function preparation on the IonQ Forte 1 machine. At the time that we ran this was the latest device that we had on Braket, and we ran what we think was the largest scale quantum compute workload that's ever been run on these systems. And so it was fitting those molecules that we saw before through that energy state transition onto the quantum computer and doing a whole bunch of sampling around that. We then moved those results over to classical post-processing using AWS Parallel Cluster, one of our high-performance compute services. And we ran the Monte Carlo simulations to find the final energy state there. We used a lot of compute to do this. We used 40 P5 EN instances. Those are the H100 instances from NVIDIA, for a couple of days running compute on here. So it was a big workload. The end-to-end state here, we think, is the largest end-to-end workload that's ever been run quantum and classical together. And the results are really, really promising. What this chart is showing on the x-axis is the system size, essentially the size of the molecules, the size of the atoms that we're looking at. So bigger and bigger molecules as we go out to the right-hand side. And on the y-axis is the runtime in seconds on a log scale. So more processing time to get there. The dashed lines that you see were the previous best available classical results that we had from this. So as these molecules got bigger, the previous best classical systems, were in those dashed lines there. The solid line is what we're able to produce classically on this hybrid workflow. So the particular solid dot that's in the middle there is this particular result, so right in the middle. So that gap between the solid dot on the solid line and the lowest level of the dashed line, that is the performance increase that we're able to get between these two workloads. And that is a 656 times speed up over that part of the processing cycle that we went through there. So a really significant result. Now, this isn't something that we could put in production. When we had to play a lot of tricks on our system to make this work, we had to learn a lot about the orchestration of running a hybrid workload on AWS. And it took a lot of compute to do this. So we can't run this in production every day. Also, we weren't looking at the cost around it. But it gives us a lot of confidence that as we're building out these systems, as we get bigger and bigger, as we're able to do more and more sophisticated orchestration across high-performance compute, that as these molecules get bigger, we're going to see a huge performance increase that we're going to be able to deliver to customers there. So as we extrapolate out to molecules like FOMOCO that are really important to problems in industrial processing and nitrogen fixation, and hopefully eventually things like fertilizer production, that we're going to be able to model these systems in a really interesting way. So I just want to remind everyone of something that Eric said right at the top of the presentation, that no quantum computer today can solve an industry-relevant problem faster, cheaper, or more accurately than the best available classical alternative. That is still true. The example that I showed you before does not yet meet these criteria, but it's a stepping stone to that. We can really see and have a lot of confidence around where this is headed. As these computers get bigger, as they get more capable, we are going to be able to tick off these things, to be able to go faster, to be able to go cheaper, to be able to do things more accurately than the best available classical alternative, and be able to do it in production over time as well. So what can you do today? How do you take action around this? Well, this is what the leading companies are doing. They're generating IP. They're generating the algorithms that will run on these quantum computers. They're generating the know-how about how to operate it in the cloud. And so you can do that too. You can get engaged with us or with our partner network and explore what the intellectual property portfolio looks like that will have an impact on your compute solutions. You can engage the supply chain. Understanding the quantum computing hardware companies, understanding the software libraries, the open source community, the partners that are out there, the university researchers that are engaged in this, having a deep understanding of where your compute is going to come from, where your algorithms are going to come from, where your software libraries are going to come from, is an important part of the puzzle. And then finally, build a workforce. Have a few people within your organization who can understand this technology, who can make sense of it for your particular organization, who can start to read the news and be able to process it in a way that's relevant to you, and be able to react quickly as computers get more and more capable over time. And so we're here to help you do that. We've got a lot of options available for you to engage with us at AWS on quantum compute. In the middle is Braket. This is an operational service in general availability on AWS today. We've been running this for 5 years. You can access quantum computers in the cloud this afternoon if you'd like. We actually have a series of workshops this week, so you can get hands-on with quantum computing in one of our workshops through the rest of these sessions. Couple of other options. We've got a digital badge available on AWS Skill Builder. You can work through a course, get a digital badge through that. Quantum Embark we talked about before for enterprise customers to engage in quantum computing. The Advanced Solutions Lab if you want to do a deeper project. And then Amazon Braket Direct is our program so that you can work directly with our hardware suppliers as well. So if you want to engage on a particular problem with IonQ or Rigetti or AQT or QEra or IQM, you can do it through that program. So a lot of different ways to engage. And then finally, just to wrap up, we've got a lot of sessions on quantum compute this week. This is just a selection. All of the sessions that we've got on quantum computer through the QR code there. But I've just put a selection on the slide here so that if you want to follow up on this and go a little bit deeper, please come to the breakout session tomorrow with JP Chase and look at the applications in the financial sector. We've got some chalk talks that go into hybrid compute, into how we're using generative AI to accelerate quantum computing software development. And then finally, a little bit more hubs, which is what Eric was talking about before with those national compute resource centers and how we're integrating in with them. So we're delighted that you can make it along today to this session to learn a little bit more about what we're doing in quantum technologies at AWS. And we hope to see you on Braket in the future. Thank you very much.